Now here, today we have machine components design, and the first part of the components design, we are looking into the designs of shafts. So the introduction here, a shaft is a rotating machine element which is used to transmit power from one place to another. Just like, for example, if you want to transmit power from an input shaft to an output shaft, it requires a shaft. Okay, so the power is delivered to the shaft by some tangential force, and the resultant torque or twisting moment set up within the shaft permits the power to be transferred to various machines linked up to the shaft. In order to transfer the power from one shaft to another, the various members such as pulleys, gears, etc. are mounted on it. Okay, so these members, along with the forces exerted upon them, causes the shaft to bend. Now, in other words, we may say that a shaft is used for the transmission of torque and bending moment. Now, the various members are mounted on the shaft by means of keys or splines. Okay, so that is the introduction of shaft. So here we are looking at the failure of shaft that is subjected to twisting moment or torque only. So this is the first part of the design of shafts. So the design of shafts actually is based on one, the strength relationship, and two, that is the stiffness relationship. And also we have to look into whether it is only subjected to turning moment only, or subjected to bending moment only, or the combine of turning moment and bending moment. So these are the three cases that we will be looking at in the later part. So in designing of shaft on the basis of strength, the following cases may be considered. So first, the shaft subjected to twisting moment or torque only. 2. Shaft subjected to bending moment only. Okay, so I hope you remember what it means by twisting moment and the difference between the twisting moment and the bending moment. Part C. So where we combine both twisting and bending, so we will be looking at the design of shaft or the failure of shaft due to the combine of twisting and bending. Lastly, shaft subjected to axial loads in addition to the combined torsional and bending loads. So the first part, we will be looking at twisting moment only. So that is torque. So based on the simple torsion equation, we have 1, the strength relationship, that is taking T here as the torque and J here as the polar moment of inertia. And tau is the shear stress in the shaft, and R is referring to the maximum radius of the shaft. So in certain cases we have hollow shaft, so then we have a maximum radius, that is the outer radius, and the inner radius. So if let's say, for example, we are looking at maximum shear stress, then the radius that we refer should be the maximum radius, that means the outer radius, if it is a hollow shaft. So T is actually the torque or turning moment in Newton meter. J is the polar moment of inertia, that is in meter to the power of 4 or millimeter to the power of 4. Tau will be referring to the shear stress due to the twisting moment, and it is in Newton over meter square, or we can say Pascal. Okay, So R is the radius of the shaft. So if, let's say, for example, you're looking at maximum shear stress, then of course this will be the maximum radius. And if, let's say, for example, we are referring to the minimum shear stress, then this term here, the radius, will have to be the minimum radius. That is the inner radius for the case of a minimum shear stress in the shaft. So that is the relationship between the shear stress and the radius. So you can see tau max, R max, tau min, you have R minimum. Now the next part we'll be looking at the stiffness relationship. So the stiffness relationship, we have T over J, G, theta over L, where G is the shear modulus or the modulus of rigidity. Theta is actually the angle of twist, and L is the length of the shaft. So T is the turning moment in Newton meter, J is the polar moment of inertia in meter to the power of 4, and G is the shear modulus or the modulus of rigidity, usually is in giganewton per meter square, so that is 10 to the power of 9 Newton per meter square or 10 to the power of 9 Pascal. So L will be the length of the shaft. Theta is the angle of twist in radians. So the next thing is we are looking at the polar moment of inertia for a solid shaft and a hollow shaft. So this is our torsional shear stress formula. Okay, that is based on your simple torsion equation. So this is the example of a solid shaft. So we have axis X, Y, and Z. So if let's say, for example, you are looking at polar moment of inertia, then you should be taking the moment, the second moment of area, or the moment of inertia about the Z axis here. So we assume that the shaft is turning about the Z axis. And the polar moment of inertia is given as pi d to the power of 4 over 32. It's not 64. If this is 64, then you will take the shaft, okay, bending about x or y axis. Okay, if let's say the shaft is bending about x or bending about the y, then this shouldn't be the j, this should be the I, x, x, or I, y, y, which is pi d for pi d to the power of 4 over 64. That is moment of inertia. But this case, this is the polar moment of inertia. So the next case is the hollow shaft. So based on the hollow shaft, as you can see, there's an internal diameter and an external diameter, and the shaft is subjected to torsion, turning moment about the z-axis. So for a hollow shaft is given, the polar moment of inertia is given as pi d to the power of 4. This is referring to the external diameter, and this the internal diameter of the shaft here. Okay, and it is divided by 32 and is not 64. Remember, you are taking it about the z-axis. Okay, so here are the examples that will be shown in the later slides. Thank you. And if there are any questions, please do ask, or you can just put in your comments on the comment section of my YouTube podcast. Thank you very much. Good afternoon. Thanks a lot.